Welcome to the final episode of the Pendulum Speed Coding Experiment with Arduino. Links to the previous videos are found in the description below. This is the fun stuff. Here you will integrate all the parts and pieces you have learned and conduct the experiment for real in the lab. Let's get started. You will need the laser and light sensor board shown here. If it is not assembled, do so now. I highly recommend that you quickly review minutes 1 through 9 of video 3 before proceeding. This video is linked above and in the description below. This video walks you through the steps of setting up your Arduino IDE for the proper microcontroller board and port. As a quick review, ensure there are no metal bits on the table. Then plug your Arduino board into the laptop like so. Next, open the IDE and make sure you have selected the proper board under the Tools menu. In our case, we are using the Arduino Uno. And select the proper port, which will be different on each computer. Hopefully, you see the words Arduino Uno associated with the port. The video is also a good reminder of how to connect 3 conductor cables from the laser and light circuit boards to the microcontroller shield. Make sure you are using the correct pin numbers as shown here in the code, and that you have properly connected the cables to these pins in real life as shown here. If you have this type of sensor shield, this is what the connections look like. An easy check is to make sure the black ground wire is connected to the ground pin labeled with a negative sign or the letters G or G and D on the boards. Ensure the microcontroller is not sitting on anything metallic, then plug it into your laptop using the USB cable. The laser should immediately light up. If the laser remains dark, quickly unplug the USB cable, rewind the video, and carefully follow all the steps to properly connect the cables. Next, ensure your laser is striking the face of the photoresistor of the light sensor. You will need to look through the long tube of the light shield to verify this. If the beam is not aligned, carefully adjust the laser alignment, or gently adjust the position of the photoresistor. We are now ready to proceed with the experiment. Open Tinkercad and copy your code from the laser and light sensor circuit. Use Ctrl-A or Command-A to highlight every bit of the code, then copy it like normal. Next, open your Arduino IDE and find your Pendulum Speed sketch. If you cannot locate it, just make a new sketch. Use Ctrl-A or Command-A once again to highlight everything within the code window, then paste your copied code, like so. Let's check that the code works by pressing the Verify button at the top of the IDE. You should see a message that says Done Compiling, like this. If you get a red error message, locate and fix the mistake. But know that if your code works on Tinkercad, it will work in the IDE. We now need to calibrate the light sensor for the classroom conditions. It is important to keep the ambient light in the room constant during the experiment. It may be best to dim the lights in the room. Locate the setup function near the top of your code. Mine is here on line 8. Uncomment the call to the print sensor command by removing the 2 slashes at the beginning of that line. If you recall, the print sensor function will continually read and print the light sensor data to the screen, and we need this to calibrate the sensor. Next, press the Upload button to load the code into the Uno microcontroller. If you get an error message like mine here, ensure you have selected the proper port. Upload the code again. It is critical that you only press the button once and that you do not unplug the USB cable during this process. However, when you see the Done Uploading message, it is safe to reload your code or unplug the Arduino from the computer if you need to. Open the serial monitor like so. And note the light sensor data streaming up the window. If the data is too fast to read, return to the code window and scroll down to the print sensor function at the bottom of the sketch. Mine is here on line 94. Locate the delay command and increase the value within the parentheses. Recall, this delay time is in units of milliseconds, so a value of 500 is a half-second delay. Re-upload the code and see if the data is now more readable. With your hand, block the laser beam and verify the output from the light sensor changes dramatically. Here, when the beam is not blocked, my sensor reads values of 12 or 13. Notice that my values for when the laser is striking the light sensor are small double-digit numbers that vary only by a tiny amount. This is desirable. If your unimpeded light readings are much larger than mine, as shown here, adjust the position of your laser beam until you get similarly small and consistent values like mine. Make a note of your own light sensor values when the beam is not blocked. When the beam is blocked, my value reads much higher than the unblocked value, as you can see. If the values differ by several hundred points, that's what you're looking for. Recall that we created a variable named light threshold and set it equal to 60. Locate this in your code window. It will be near the top of the sketch. Mine is found on line 5. Change the threshold value to match the lighting conditions in your classroom. We want the timer to start just as the cylinder enters the beam, so set the threshold to a value about 5 or 10 points bigger than your biggest unblocked value. Since my largest unblocked value was around 15, I set my threshold value to 20 as shown here. When that is done, once again comment out the call to the print sensor function. Do so by adding the 2 slashes like so. Upload the code once again to run the Pendulum Speed section of the code. Open the serial monitor so we can see the code's output. Secure the pendulum to the pendulum clamp like so. With the pendulum hanging vertically without swinging, slide the speed detector so the pendulum rests within the space between the tall screws. If the wires are getting in your way, put them in the wire chase and secure them with the little cams like so. Make sure the laser beam is not hitting at the very bottom of the pendulum, like this. If that happens, simply loosen the clamp holding the string and lower the pendulum an appropriate amount, like so. Line it up so the laser beam hits the center line of the pendulum. It is likely that the laser will strike near the bottom of the cylinder, and that is fine. But try to get the laser to hit along the pendulum's center line, like so. Next, gently pull the pendulum out a few degrees to allow the laser beam to impact the light sensor. You should see the statement, "Ready to release the pendulum," on the serial monitor. Make sure that you lift the pendulum only by a small amount. If you pull it way back, it could swing sideways and crash into the microcontroller, and that would be bad. Gently release the pendulum so it swings directly through the laser beam without crashing into anything. Try to catch it as it reaches its peak on the other side. Note the speed of the pendulum and the serial monitor. How cool is that? Seriously, think about what you just did. You just made a photogate speed detector for a fraction of the cost of a similar commercial device. I looked up the prices of the top 2 commercially available photogates, interfaces, and software, and the average price was just under $340. Our homemade device of the Uno diode laser, voltage divider board, and light sensor cost only $34, which is a 90% savings. And you learned a new skill. The code is still running, so let's do it again. Lift the pendulum a little higher and release it, catching it once it swings through. Hopefully, the speed at the bottom of the swing is a little bigger. Why is that? Use your physics knowledge to explain it to yourself. To get consistent speed measurements, you can use a reference block, such as this Rubik's Cube, to ensure the pendulum starting point is the same each time. Notice how I ensure the bottom of the pendulum just touches the top edge of the cube before releasing. As you can see, this method produces very consistent speeds. Finally, pull the pendulum back, release it, but this time do not catch it. Over time, what happens to its speed? What should happen to its speed? Again, use some physics to explain this phenomenon. Also notice that the speed is always positive no matter which direction the pendulum swings. In other words, our sensor does not and cannot determine the direction of motion. So we are measuring speed, not velocity. To get the direction, you would need 2 photogate sensors. Congratulations on a job well done. At this point, some of you may be happy to be finished with the coding section, but others are just getting excited about the possibilities. If you fall into the latter category, consider working on these bonus exercises. Number 1, write code that will turn on the microcontroller's onboard LED while the pendulum is blocking the beam, like so. While we only briefly discussed this way back in our first lesson on kinematics coding, all the code you need to do this is created anytime you create a new sketch on Tinkercad with an Arduino Uno board. Here's the code to turn on and off the built-in LED. And don't forget that you will need to add a pin mode command in the setup function. Bonus problem number 2. Now that you know the pendulum speed at the bottom of its swing, write code that will calculate the theoretical initial height of the pendulum when its speed is 0. Here's a hint. Use the principle of conservation of energy and assume there is no loss of mechanical energy during the swing. Here is what my output looks like as the initial height increases with each swing. Here's another hint. Define the height at the bottom of the swing to be 0. Set up the physics problem on paper and derive the equation yourself. Do you need to know the mass of the pendulum for this calculation? I don't think so. Bonus problem number 3. Imagine that you always release the pendulum from the same height, and that you measure that height with a ruler. You can then code in that initial height and calculate the percent difference between the height measured with the ruler and the one calculated by your code in the previous bonus problem. Don't forget to account for the pendulum's height above the ground at the bottom of the swing. As you can see, my sensor gives initial height values that are only off by a few percentage points with each swing. Not bad for a device that costs practically nothing. Other things you can do in the world of physical computing is build a gripper that will release the pendulum for you, or use a sensor to measure the initial height for you, or compile lots of data for you so you can graph it in Excel, or dive deeper into programming and code in the linear regression equations to calculate the slope and y-intercepts for you. The list is nearly endless. Well, I hope this foray into computer coding and physical computing has been interesting and rewarding for you. I also hope you see that there's practically no limit to what you can accomplish, even with some basic coding skills and rudimentary, inexpensive equipment. If you want to go further, I recommend that you find a project of interest and try to write code to solve it. For example, have the computer solve your math homework, or stoichiometry problems in chemistry, or unit conversions, or financial calculations, or even write a text-based D&D adventure game. These are all projects that got me started in 1980, and they may also be fun for you. However, you have the benefit of textbooks and the internet to help you. Until next time, take care and thanks for watching.